In this video, we're going to discuss the very important concept of linear independence and dependence. These are properties that sets of vectors can have. Before we just define it, I think it's a good idea to just do some motivating examples. So we're going to do 3 examples, just get a feel for the kind of things that we're interested in looking at, and then we'll make the definition clear, and then we'll look at our examples again to see how to apply the definition in the cases that we discussed originally. So here's our first motivating example. I'm going to let u be the vector 2, 1, and I'm going to let v be the vector 4, 2. You may be interested in understanding the span of these two vectors. Remember, that's the set of all linear combinations of u and v. If you were to plot the vectors or just look at the numbers, you'd very quickly realize that these two vectors are parallel to each other. If I draw the vector u and then draw the vector v, it looks like it's just twice as long as my original vector. Therefore, the span would just consist of all the vectors parallel to either u or v, in which case it seemed redundant to include both the vectors when describing this set of vectors, and in fact we might have just written span of u, or if you prefer, span of v, or the span of any non-zero vector parallel to those. What's happening here algebraically is that twice u is equal to v, and you can just see that by inspecting the coefficients here. If I double u, I'll get the vector v in return. If you prefer, you could solve for u, and 1/2 times v would be equal to u. That's an equivalent expression, an equivalent relationship between these two vectors, an equivalent way of stating how they are dependent on each other. If we wanted to write it in a way that wasn't so preferential to one vector or the other, I might solve for 0 on one side and write it as a homogeneous expression. So now I have u minus 1/2 is equal to 0. What we're saying is something about the following homogeneous vector equation. If I scale u and I scale u and I form a linear combination and I get 0, there must be non-trivial ways of doing this. There are coefficients that are not all 0 that I can put in front of u and v to get the 0 vector. In this case, it has non-trivial solutions such as x1 equal to 1 and x2 equal to minus 1/2, what we saw in this equation here. I have a weight of 1, I have a weight of minus 1/2. Those are non-trivial solutions to this homogeneous equation. Let's look at a second motivating example. I'm going to let u be the vector 2, 1. I'm going to let w now be the vector 2, 0. It's pretty clear if you scale one of the vectors, say if I take w and I multiply it by some scalar c, then I'm never going to get the vector u in return. For example, if I was going to scale 2 here, the first entry of w, to get 2 here, I had to have scaled by 1. But if I scale 0 by 1, I won't get 1 in return. I'll still have 0. So u is not a scalar multiple of w. There is no c that I can multiply w by in order to get that vector u. If you think geometrically, you can see that these vectors are not parallel to each other, and that's pretty significant here. Particularly in 2 dimensions, it means they're pointing in significantly different directions, so that when I look at the span of these two vectors that are not parallel to each other, I would expect to get the entire plane, and that's something you could readily check. The span of u and w is equal to r2. Let's think about it in terms of the homogeneous equation, motivated by what we saw in the previous example. If I look at a linear combination of u and w and I get the vector 0, are there any non-trivial weights that I could put in front of those vectors to achieve this? And the one answer is, of course, I could always put 0 in front and 0 in front and I would get 0. This is what we call the trivial solution, but that's not an interesting relationship between those two vectors. And in fact, this homogeneous equation has no non-trivial solutions. If there was at least one non-zero number that I could put in front of u and w, then I could solve for one of them, and it would have contradicted our observation above that they are not scalar multiples of each other. So the homogeneous equation in this case has no non-trivial solutions, so in a sense these vectors are somewhat independent of each other. Let's look at a third example. I'm going to let v1 be the vector 2, 1, v2 be the vector 2, 0, and v3 be the vector 6, 2. If you just look at that vector 6, 2 and maybe think about it for a moment, it may not be entirely obvious, but there's some relationship between that vector and the other ones. It's not simply that I can scale one of them to get that vector. For instance, if I take v1 and multiply it by 3, I'm not going to get this vector 6, 2. If I take this vector here and I multiply by 3, I'm not going to get the vector 6, 2. So I'm not claiming that these two vectors are scalar multiples of each other in different ways. It's a little bit more subtle. In fact, if I look at the vector v and I double that one, and then add to that result the vector v2, so I'll have 2, 0 here, and I take one of those, there is a linear combination of those two vectors that gives me my third vector v3. So it's not just about scalar multiplication here, it's about are there linear combinations of some of the vectors that get me other ones of my vectors. And in this case there is. Let's write this symbolically. v3 is twice v1 plus v2. You might write that in a homogeneous fashion just based on our previous discussion. So I'll solve for 0 on one side and I have 2v1 plus v2 minus v3 is equal to 0. What we're saying is that the homogeneous equation, where on the left-hand side I have an arbitrary linear combination of my three vectors, on the right-hand side I have 0, this must have some interesting solutions to it. Of course, I could always put 0, 0, and 0 in front for the x's, and I would have a trivial solution to it, but we're seeing here that there are non-trivial solutions to this vector equation. For example, I could take x1 to be 2, I could take x2 to be 1, and I could take x3 to be minus 1.